Hello everyone. It is really a pleasure for me to be here and present our paper, Federated Bandits with Personalization. My name is Chen Shuaishi, and I'm currently a second-year PhD student at University of Virginia. This is a joint work with my advisor, Professor Cong Shen, and also Professor Chen Yang from the Pennsylvania State University. In this presentation, I will start with the motivation part and then introduce the framework and problem formulation. After that, a lower bound analysis will be first presented. Then, I will give a brief illustration of the algorithm design. Last, theoretical analysis and experimental results of the proposed algorithm will be provided. Without further ado, let's get started. Federated learning is a recently proposed distributive machine learning scheme that has a few interesting characteristics. For example, it can handle distributed learning with non-ID local datasets. Recently, some attempts have also been made to bring the key principles in federated learning into the study of multi-bandits. A so-called federated multi-bandit framework is proposed. Taking the cognitive radio system in the figure as an example, the base station, which is the server here, wants to learn the global channel availability over the entire caved area for control signal broadcasting. But it is fixed at one location and thus cannot directly measure the desired global channel availability. On the other hand, clients have heterogeneous local bandit games, and they can directly interact with the local bandit games and collect local observation. With the cognitive radio system as an example again, local clients, which are local devices here, they are at different geographic location and they face different local channel availabilities, and they can collect statistics of this channel by communicating over them. Back to the server side, since it cannot learn the global model itself, the global server wants to use information collected by local clients to solve the global learning problem. However, it is often the case that local observation can only provide partial information of the global model. For example, the local channel availability of each client only characterizes the wireless environment at that location, but it cannot represent the entire caved area. Thus, neither the server or the single client can learn the global model by itself, which means coordination between them becomes essential, just like in the standard federated learning. Like I just said, these current attempts are almost all focused on helping the server learn the global model. In other words, they are fully focused on generalization. However, only learning the global model is often not sufficient in practical application. Specifically, the globally optimal action is often suboptimal or even very poor from the local perspective, since it ignores the needs of personalization. For example, ARM 3 is the optimal ARM globally here. However, it has a very poor performance of local model 1. This similar needs of personalization is also recently recognized in the study of standard federated learning. To better trade-off between generalization and personalization, we propose to study federated multi-bandit but with personalization. So, let's talk about the personalized federated multi-bandit framework that we propose. In this framework, there are M clients, and each of their local models has the same set of K-arms. In previous cognitive radio system example, the clients are local devices and the arms are different channels. However, the arm statistics are heterogeneous across clients. Namely, we denote the expected reward for client M's arm K as μKM. Besides the clients, there also exists a server which faces a global bandit game that also has a K arms. We further denote the global expected reward for arm K as μK, and we assume that the global arm statistics are the exact average of local arm statistics. Specifically, μK is the exact average of μKM. As I mentioned a few slides ago, the key constraint in this framework is that the server itself cannot directly interact with the global model, so no one gets the global information directly. The first extreme of the learning objective is often to focus only on the global performance. In other words, full generalization but no personalization. Such global performance can be measured by the global cumulative reward here, and obviously, the optimal choice in the global optimal arm. The current Federated multi-bandit study are mainly focused on this part. The other extreme is of course to focus only on the local performance, which means full personalization but no generalization. Similarly, the local performance can be measured by the local cumulative reward labeled in blue here. The optimal choice now is simply the individually local optimal arms for each individual client. It turns out that this is actually captured by the standard MAB studies. It can be effectively solved by letting each local client run UCB or Thompson sampling algorithms individually on their own. However, as we know, these two objectives are often contradictory with each other in practice. So how can we balance or trade-off between them? For this purpose, we designed a new mixed learning objective. It is the weighted sum of the global-only and local-only objective. The parameter alpha here let us smoothly balance between the two extremes. When alpha is set to be 1, it returns to a local-only setting and only cares about the local performance. When alpha is set to be 0, it then becomes a global-only objective. When alpha is between 0 and 1, the two extreme settings are both taken into consideration and thus results in a mixed learning objective. Now we have the mixed learning objective, and we further construct a hypothetical mixed model based on this objective. It contains a mixed reward, which is also the weighted sum of global and local rewards with alpha. For an expression of its mean value here, we can see that it contains both local information and also global information. This leads to the key challenge of the problem that global information can actually not learned by individual clients and has to be provided by all the clients together. So coordination here is also required. With respect to this mixed model, we generalize the regret definition. Note that besides the standard term of loss from arm sampling, an additional term here is imposed to count the communication loss. With this PFMAB framework, let's first take a look at its fundamental limits, the lower bound. Due to the time limitation, I'm not going to dig into this theorem here. However, the key philosophy here is that it contains the blue term for local exploration and the green term here for global exploration. The minimum and maximum labeled in red here take the worst case among all losses. We also know that this is not a universally tight lower bound, and would be very interesting to see some further investigation on how would the true lower bound behave, especially its dependency on alpha. Inspired by the lower bound analysis, we designed the Pfucp algorithm. We summarize 3 key principles here. First, clients have to be selfish now, since local performance is also taken into consideration. Second, they also need to be generous by learning global model to help others. Last but not least, to avoid a high communication cost, clients should talk less and do more. Specifically, they should only communicate periodically when sufficient local information is collected. This is similar to the periodic communication in federal learning studies. The Pfucp algorithm proceeds in phases. Here's a brief sketch of one phase P. It starts with the global exploration subphase. In this phase, all clients will explore the arm in the global active arm set to get global information. After that, the local exploration subphase begins. Namely, each client explores arms in their own local active arm set. Note that, unlike the homogeneous global active arm set, the local active arm sets can be different for different clients, since due to the client heterogeneity. Thus, after one client finishes exploration, they will first upload their collected local statuses to the server, and then they will enter the waiting phase or the exploitation phase to wait for the other clients finish their exploration part. In this exploitation phase, they will keep pulling their empirically best arm to avoid high loss. After all clients complete exploration and uploading, the server will aggregate local information into the global information and send this information back to the local client for there to make future decisions. The phase P then ends here and a new phase begins. Here, we provide some performance analysis for the Pfucp algorithm. First, theoretically, it has an order-optimal regret behavior, which is of order log t here. From the theorem here, we can also see that it has two parts. It contains a loss from local exploration, labeled in blue here, and a loss from global exploration, labeled in green here. More importantly, when we set alpha to be 0 or 1, this regret upper conf bound can be returned to the results of the two extremes. Experimentally, using the movie lens data sets, we can see that with different value of alpha in the figure on the left, Pfucp has a very stable performance. And from the right side figure, we can see with the change of alpha, the average reward of the mixed model, which is the blue line in the middle, can smoothly balance between the two extremes. Such smooth transferring allows us to trade off between the two extremes and allow a flexible learning objective decision. As a conclusion, in this paper, we propose the PFMAP framework to trade off generalization and personalization. In the design of Pfucp algorithm, we carefully balanced between global exploration, local exploration, and exploitation. Theoretically, we performed a lower bound analysis for this framework and proved an order-optimal regret behavior for the design algorithm. There are still a lot of interesting open problems in this new field of federated modern bandits, and we look forward to seeing more investigation of this exciting topic. Thank you for your time.